because the source itself is an incoherent source, so it's not a coherent source. So it's like a flashlight. So you have to limit that to either placing a collimator, perhaps to make it just para, or the space shuttle can be controlled through the opening that you place on the. So that's
All
how
right.
we
So
control the
yeah.
spatial resolution of the treatment. Yeah.
So typically, what is the dimension of the aperture or slit? So this in 100 microns or centimeter?
No, it's in the millimeter. So it's around, it's just the size of one well plate. So it's around 1 cm or 10 millimeters or so.
All right.
Yeah.
All right. Thank you. Any questions from the panel?
Sir?
Yes,
Uh,
Vanessa.
Yes,
Vanessa.
Vanny
Uh,
Balois from RIKEN, Japan. Thank you for the very nice talk, Dr. Mel. Actually, I have a question particularly about the gold nanoparticles. So the first question I have is, what concentration do you need to put? How much gold nanoparticles do you need to put on your cell array in order to detect or in order to neutralize the colon cancer using your method?
As you can see, the way we've done it, since the absorbance is detected at 570 nanometer,
Mm-hmm.
that means we have a background, it's like an autofluorescence. We have a background signal
Yes.
coming from the gold nanoparticle itself. So
Yes.
so the way we measure the viability of the cell might not be the optimum
Mm-hmm.
way of detecting the effects of the gold nanoparticle, because we
Yes.
use a fluorescent dye,
Mhm.
which is also near the autofluorescent signal of the gold nanoparticle. So
I
that's why
see.
we cannot see. And you would see there's a elevated absorbance value at those. So
Mhm.
well, based from our measurement, the cancer cell proliferated. So that means it multiplied instead of reducing.
Yes.
But of course, that might be a false signal, because maybe the uptake of the gold nanopar was not really did not really attach to the cancer cell. So I think there's still a lot of work to do there, because these are preliminary work we've done in the lab,
Yes. Mm-hmm.
and we're just starting to see the problem that's facing us. So perhaps we have to use other means of detecting the viability of the cell for this case.
Okay. Thank you. Can I ask one more question? So the
okay.
second question is more on making the gold nanoparticles. So when you create the gold nanoparticles, they have a tendency to aggregate over time. What do you do? Do you put some surfactant or
No,
some other molecule to prevent them from aggregating?
that's actually a good question, because that's the problem that we encountered, the clustering. So if
Yes.
you know, and that's what we failed to do. We did not place any surfactant in the, so
Mm-hmm.
that they could disperse,
Yes.
because these are colloids. These are gold nanoparticle colloids. So as
Yes.
I mentioned, these are just preliminary work, and we're just discovering some of the things that we have to overcome when we do this kind of research.
Okay, thank you very much. And it's a very exciting research, and I hope you become successful in your future
Yeah.
work. Thank you.
Oh, thank
All
you,
right.
Vanessa.
So we
I
have another question from Dr. Hermosa.
good
Hi.
morning. Good morning, Mel. It's a
Hi.
nice talk. Um
Thank you.
okay. My question is, okay, you tested this for cancer cells, right? And
Yes.
there's a specific gene that you are targeting. Um ha- I don't know, I'm new in this field, so I don't know if what is the effect in normal cells of this RF ablation.
That's a good question, but this is outside our experiment. But we've done this to other cancer cell, like breast cancer cell line, with we call it the normal the normal cells, and it's highly selective. If we use the same treatment with this breast cancer cell line, normal cell did not die at all. But if you can tune actually the frequency, specific frequency, then the cancer cell are actually, you can see them die at specific wavelength. So we're just suspecting maybe the mechanism is highly selective to a particular kind of cancer cell.
Okay.
And we're looking at the gene level. That's why we want to pursue gene expressions for different kind of cell, like this one that we identified already 3 genes. So perhaps by monitoring that, so we want to know if that is really affected by the treatment or not. So because those are the genes that are mutated, genes between normal and the cancer cells. So those are the genes that are they are mutated compared to the normal cells. That's why we want to look at that. Perhaps there might be a relationship.
Yeah. Okay. Second question, in relation to my first question. So if this is electromagnetic field and it is impinging on your cancer gene, so does it mean that there is a somewhat a chromophore or something that absorbs or is sensitive only to that particular frequency in a cancer cell, so that could distinguish it from a normal cell?
That we don't know, but as far as I know, there's a very complicated mechanism on why there is an apoptosis or even necrosis that happen, and we want to see if it is really coming from the cell itself, or there might be a mitigating agent that would trigger the apoptosis and necrosis of the cancer cell. So we're looking at that. But when you say chromophore, I think that would be a good idea if we can do that, because there's a new technique on how we can detect it non-invasively in the future. So that's a fantastic idea, actually, if you see it that way. It's possible.
Thank you very much.
All right. So other questions? Mel, perhaps towards the last, how much, or what is the maybe the limiting element in your setup? That meaning, if you don't have that component, you cannot do your experiment. How about the gold? Is it? Are there alternative to gold nanoparticles?
Yes, there are some, but the silver nanoparticle would be another alternative in terms of cost. But the silver nanoparticle have its own antimicrobial activity, and we don't, which is also good, because one of the enemy actually of cancer cell are the other pathogen that might kill it. And it's so sensitive, and that's the irony of it. When you're exposed to an in vitro condition and just one tiny pathogen, it would kill the cancer cell immediately.
All right. So thank you, Mel, for the presentation. So we will now move on to the next presenter. I will ask Ms. Ritz and Aguilar. Yeah. So we will now go up. Can you start your screen sharing, Ritz, if it's working? And also the audio. I haven't heard your voice.
Hi. Can you hear me?
Okay. Yeah. So you can start sharing the screen. All right.
Okay. So good morning, everyone. Thank you for the invitation. It's such an honor. Okay, so my talk is about computational ghost imaging, principles and applications. Again, I'm Ritz from the National Institute of Physics, UP Diliman. Okay. So when we think of the word imaging, let me start with this one. When we think of the word imaging, what we usually have in mind is smartphone cameras or compact system cameras, also known as mirrorless cameras or DSLRs, right? So when we try to remove uh, for example, the lens in here, what we'll directly see is the imaging sensor, which is the one that's converting electrical signal to optical signal. So it's usually made of a CCD chip or a CMOS chip, and that looks like this. So it has RGB components, and usually they have a range from 1 megapixel to 24 megapixels nowadays. So it's made of an array of detectors, and there's an electrical circuit that's embedded within it that's converting the light signal to an electrical one. So that's usually how it works. So when we say when a CCD chip, for example, has a resolution of 1 megapixel, that means 1 million single pixel detectors or 1 million photo detector units. And that's why they're usually expensive to build. Now, what if we take just a single unit, a single photo detector unit from these millions of photo detectors, and then we use this single pixel detector or this photo detector unit to image something, and how will that work when you only have one detector out of millions of detectors? Now, with this technique called computational ghost imaging, what it does is to pass on the two-dimensionality of the detector array to your light source through the use of a spatial light modulator, for example, which modulates the intensity of the light source or the phase. In this case, what we need is to modulate the intensity of the light source. To say you have a classical light source here, or even a quantum source, a laser source. So what you do is to pass on or to pass on this light source here to your spatial light modulator, and you modulate the light by producing several structured patterns, and you project this into your object. So for example, for this one, it's a transparency object, and you use a single pixel detector. In this case, it's a bucket detector, which collects all the transmitted light from this transparency, from the combination of this modulated light with that of the transparency object. And then from the correlations between this modulated light and the signal collected by the bucket detector, you'll be able to form uh, the image of this object. So a ghost image is actually an image that's retrieved using a computational ghost imaging or a single pixel imaging system. So it only needs a single pixel detector and a modulated light source. So those are the only two things that you need. Instead of having millions of detectors, you only need one. But then again, you need your light source to be modulated in terms of intensity in this case. Okay, so for a computational ghost imaging, for a formal definition, it produces images using a bucket detector instead of an array of 2D sensors, and it uses a spatial light modulator to generate programmable illumination patterns onto the target scene. So it has several advantages actually over the conventional imaging, which uses detector arrays. So one is that it's adaptive in most environments. Number two, it has a flexible light path configuration. You can have a reflective um, type SLM, for example, to image a reflective type object instead of a transmissive one. It's capable also of non-line of sight imaging. So the bucket detector or the single pixel detector just collects all the light, reflected light from the target scene. And so it does not need to, or the single pixel detector rather actually does not have to face the target scene itself, unlike with conventional imaging wherein the imaging sensor and the lens actually has to be in line with that of the target object. And it can also have high signal to noise ratio, well, depending on the algorithm, the computational imaging algorithm that you're going to use. But the disadvantage of this one over the conventional imaging, which uses detector arrays, is that it has a very long computational time, since it only uses a single pixel detector. But again, you can have several image retrieval algorithms, for example, compressive sensing, to reduce this computational time. And most of the time, it's still expensive because of the use of SLM. But actually, you can build one which is very cheap depending on the components that you're going to use. So for building a single pixel camera, we can actually build a low cost one. Okay, for the stages, so the first one is you build the lux meter or the intensity meter first, and then you can proceed on to sensor characterization. Just like with any imaging system, you need to do this, and then you also need to calibrate the entire system, entire imaging system once you've collected the components and combined them to form the setup. So for the first stage in building your single pixel camera, you need to have a lux meter. So for this one, the components are, of course, a single pixel detector. You can have a light dependent resistor, an LDR, which is very cheap actually, and it only costs around 10 Philippine peso. It's widely available. It's sensitive to light intensity changes, and yeah, and again, it's very cheap. And the other component that you need to build a lux meter is the analog to digital converter. You can use an Arduino board, for example, uh, to convert the optical signal collected by the LDR onto an electrical signal. So it has analog pins, as you can see here, and then it also has an input voltage. Usually it's constant at 5 volts, and then of course the ground. And then you need to have a resistor to usually impede current flow. So um, after collecting these components, you can build your lux meter prototype that looks like this. With an LDR, you can make a very simple voltage divider circuit, and this is already proportional actually to your intensity signal. So this one here, in the lux meter prototype, what I have here is just the LDR and the resistor connected in series to form the voltage divider uh, circuit. All right. Now, for the second stage, of course, you need to characterize the sensor or calibrate the sensor itself. In this case, with this one here, the boxed area is the uh, lux meter system or the voltage divider system. Its output voltage is connected to a data acquisition system, say an oscilloscope, and then you have a light source here, which is an LED connected also to a resistor. And then you feed a square wave, for example. So for this part here, what we want to show or what we want to do is to see or to compare the input signal coming uh, from the square waves or from the function generator, and then compare that with the output that's detected by your light dependent resistor. So again, this one is a square wave. Now, because LDRs have a slow response, what we expect to see is not a square wave, but a modulated square wave actually. So this is a setup for sensor characterizations. You have your input and output. We want to compare the two. Uh, this is the input square wave, the one in black. And as you can see here, the red plot is the output detected by the LDR. Again, it's slow. It takes time to reach a saturation signal or a constant signal. But from there, you can actually extract the time constant. In this case, it's around 25 milliseconds for the LDR that we use in our experiments. The time constant or the time it takes to reach a saturation value or a constant value is at 25 milliseconds, which is kind of slow, but it's already good. Yeah. So after obtaining this time constant, you already know the time delay between the projection and the capturing based on the on the time constant actually of the LDR. So the next step is to do system calibration, wherein you project increasing gray levels on a wide screen, and then you obtain the voltage reading. So as you can see here, LDRs have a nonlinear response. So this is a voltage as a function of gray level, which is proportional to intensity level. And this plot tells us that it's best to image at low light levels, because it's this region is the most linear, and therefore it's the most sensitive. And this can also be an advantage, because even if you have a dark environment, the LDR is still able to capture the signal with a relatively high signal to noise ratio. So again, this is the LDR's voltage response to changing light levels. So after you've built the lux meter, you've characterized the sensor, you've calibrated the entire imaging system, you can now build your experimental setup. So in our case, our spatial light modulator is just a commercial projector. And then the ADC here is again the Arduino board. The single pixel detector here is just an LDR, which is very cheap. And then we employ a particular technique called Fourier ghost imaging, wherein we project sinusoidal patterns, series of sinusoidal patterns onto the object. And for each pattern, light signal is collected by your single pixel detector, and then the signal gets converted. The analog signal collected by by the single pixel detector is converted to a digital signal using your Arduino board. And from the correlations of the illumination pattern, or of the structured patterns, and the collected signal by this LDR here, you can combine all of these signals to retrieve the image of the scene here. Um, just a brief explanation about Fourier ghost imaging. So it just uses the knowledge of Fourier transform, and utilizes knowledge that most of the information of natural images are located in low spatial frequency bands. For example, here, these are standard images being used for image processing. This is the Fourier transform, the 2D Fourier transform of these images. As you can see, the power spectrum is concentrated on the low frequencies. Okay, so this is a Fourier spectrum. So this tells us that it's sufficient to actually image the low frequencies, and then from there we'll be able to see most of the details already of the object. So what you do again is to project sinusoidal patterns, and from there extract the reflectivity, the total reflectivity of the object from the combined um, uh, signals from the structured patterns. So for the results, so here's a sample test object, the UP1, and from the calibrated imaging system, computational ghost imaging system, which is a very low-cost one with the use of LDR and a commercial projector. This is the sample result that we have obtained for a 1% for a spectrum, and then 10% for a spectrum. By taking the inverse Fourier transform of this one, uh, we were able to see or reconstruct the image of UP here. So at 1%, you can already see the details of UP, and even at 10%, um, we can see a clearer image of UP, although it's kind of noisy because of the absence of a focusing lens. But to increase the signal to noise ratio, you can actually place uh, collecting lens or a focusing lens in front of the single pixel detector to at least increase or to reduce the noise signal and increase the SNR of the system. So here, the lensless FGI system is capable of sub-Nyquist sampling. The results have been published actually just last year in American Journal of Physics. So my co-authors here are Doctors Nathaniel Hermosa and Maricor Soriano. So to summarize that part, we were able to we propose and demonstrate a method for lowering the cost of computational ghost imaging setups by employing cheaper devices such as commercial projector and a light dependent resistor, the proposed imaging system produces good reconstructions of uh, the test object even at 10% spectral coverage, which is well below sub-Nyquist sampling. For the other part of my talk, it's just a simple extension actually of the 2D ghost imaging. So if you add a few more resistors, you can do 3D ghost imaging or 3D computational ghost imaging. So we have this technique called photometric stereo, wherein you have multiple light sources, for example, and then just a single camera capturing the light reflected by a sample seen from each of these light sources. So for a modified version of this photometric stereo system, what you can have is that you invoke Helmholtz reciprocity, which tells you that a light ray and its reverse ray undergo a match optical adventure. So at the location of the light sources, you can place your cameras, and then at the location of the camera, you can place your light source, and then we can use our single pixel detector system to retrieve actually uh, a 3D the 3D structure of the scene from the shading information collected by the shading information collected by each single pixel detector. So the camera here is a single pixel detector. All right. So for the mathematical formulation for that one, so first what you want to do is to define the albedo scaled surface normal. So let me just go back here. So the surface normal vector is this one, for example, for this particular point on the surface, and you want to record this one for all the points on the sample scene or on your target scene. Okay, so the normal vectors will actually give you later on the 3D shape of the object. Um, after representing the albedo scaled surface normal, what you can do is to extract the intensity or collect the intensity and recast that collected by all detectors and recast that into a matrix form that looks like this. We solve for this um, variable here using matrix inversion, linearly squares algorithm. And then we have this formula here for solving GJ. And then from there, the surface normal and sub J can be extracted. And this one here is what you need to extract the 3D shape of the object. Using this algorithm called semi-calibrated photometric stereo, if the light magnitude is unknown, for example, that's hitting the single pixel detectors, but the positions of the detectors are known, we can invoke a minimization technique to extract or to optimize the lighting parameters here. We can reduce that or we can further employ a non-linear least squares approach called the Levenberg-Marquardt algorithm to optimize the lighting parameters. After optimizing, we can then solve for the surface elevation from the extracted surface normal earlier, and then from there just use a line integral to extract the 3D shape of the object. Another method which we do to lower the signal to noise ratio, to increase rather the signal to noise ratio in the to the images first before employing the SCPS or semi-calibrated photometric series algorithm is to apodize the 2D images, which means to remove the foot, or mathematically it's remove or smoothen sharp discontinuity in a mathematical function. So here we use a Gaussian filter. We multiply it to the noisy spectrum. um, it has this form here. It's a 2D Gaussian function the sigma here is the standard deviation of the Gaussian distribution, and then you can play with this value before multiplying it um, with the 2D Fourier spectrum, with the 2D Fourier spectrum collected by the single pixel detectors. So for the experiment, of course, what you do first is to calibrate the detectors and the entire imaging system. You obtain the Fourier spectra using the 3D imaging system. We apodize each spectrum to minimize noise artifacts, and then we apply the semi-calibrated photometric stereo technique, which optimizes the lighting parameters from the images themselves, and then we display 3D. Here we compared four techniques. The direct photometric stereo, is an uncalibrated system. It just assumes that the light magnitude collected by each detector is the same. For the one with the plus A, it employs the apodization technique, which is a multiplication of the Gaussian filter for noise reductions. All in all, there are four cases. So this is the built experimental setup for 3D computational ghost imaging. We have 6 LDRs here. You only need at least three. You only need actually at least three, yeah, to collect signals from a sample scene. For the calibration part, so as you can see here, these are the calibration curves collected by our system for the 6 single pixel detectors. So even if they were manufactured in the same way, as you can see, there are still discrepancies, which means that they have differing sensitivities, and which tells us that the light collected by the LDRs may not, the light magnitude collected by the LDRs may not be the same. And so we can use the semi-calibrated photometric stereo algorithm to solve this problem of differing sensitivities. For the objects, these are simple ones. We just wanted to show or to build up to show rather a proof of concept actually for this 3D CGI. We have here a hemisphere, a cone-shaped object, and a 3D sine wave object. Okay. Um, so for the results of the apodization, so each detector is actually obtains the spectrum first. We apodize the Fourier spectrum, which shows us that after apodizing, we can actually minimize the noise collected by the detectors. Um, and then after that, as here is a sample effect of apodization on the noisy images. So starting with um, a standard deviation for the Gaussian function of equivalent to 1 up to 0.1. So here, as you can see, as sigma reduces again, okay, we as sigma reduces here, the radius of the Gaussian mass, of course, reduces as well, and we see that the reconstructed image by the LDR has now better or higher signal to noise ratio. So we're essentially cleaning the image before feeding it to the photometric stereo algorithm. So as you can see here, for the cone object, we were able to clean it with the apodization technique as well as with the sine object. And upon combining and then applying the photometric stereo technique, let me skip this one. These are sample 3D images for the four cases. So with the direct case, the images are tilted because of the differing sensitivities of the LDRs. Um, and then there are corrugation artifacts because of the noise. But upon application of the apodization technique, as you can see, we were able to clean them. And then applying the semi-calibrated photometric stereo, we were able to remove this tilt due to differing sensitivities and exposures. And then finally, with the semi-calibrated photometric stereo algorithm plus the combined with apodization, we were able to create accurate 3D images of the cone, the hemisphere, and the sine wave object. So here is a sample 3D view of the object, rotated 3D view of the cone object. So as you can see here, the best one again is the combination of the semi-calibrated case plus the apodized cases with the following percent errors. So for the semi-calibrated case without apodization, it's kind of high because of the noise artifacts. But if we apodize them or if we clean them before feeding it to the algorithm, we were able to obtain a low percent error of 6.86%. Okay. So uh, we can also evaluate the intensity error maps obtained by the system by evaluating this or by evaluating G, the albedo scaled surface normal estimated using the photometric stereo algorithm. As we can see here, again, the semi-calibrated plus apodized case gives the best results. So this is actually a plot of the root mean square error across all the images captured by all detectors for each case and then for each object. So the lower the values, the better, right? So finally, to summarize, we achieve 3D computational ghost imaging with multiple photoresistors serving as single pixel detectors using semi-calibrated lighting approach plus apodization technique. The system does not need special calibration objects or additional optical components to perform accurate 3D imaging, making it cheap and adaptable. And of course, it can also be used or for applications outside the visible spectrum. So that's all for my talk. Thank you for listening.
All right. Salamat, Rich.
Okay.
So if you have, for the audience, if you have questions, you can type in your questions at the chat box and Q&A box. Okay, so any questions from the panel? So maybe I can start. Uh, the output of the computational processing is a complex field, right?
Yes, sir. Yes, sir. It's complex.
Complex, right?
Uh-uh.
So what could be the interpretation or the significance of the phase of the complex field?
We haven't looked into that yet. Actually, the face part. Before, I tried actually extracting the face and use that to uh, extract the 3D shape from the object using this technique called Fourier transform profilometry. Like it's like an analogy, but the 3D shape that was extracted using the face that was captured by the system was kind of noisy. It was not good. It has lots of discontinuities, and so I'm not sure what I was doing wrong. But I can look into that further. Actually, the face part that was
Yeah.
captured. So for now, I'm
Uh,
focusing on the on the real part. Yeah, the magnitude.
Actually, the noisy distribution is expected, di ba? Kasi it's a optically rough object. So
Yes, yes.
maybe we'll have some uh, meaningful, significant uh, signal if maybe you do some comparison of phases. So like
Um,
an initial state and then final state, you do the phase subtraction. Maybe it will reveal correlation between the phases. So just maybe something to try.
yeah.
All right.
But actually, uh, the main source of error for this one, actually, as you can see, it has a very noisy background. It's probably the absence of a collecting lens or a focusing lens in front of the single pixel detector. But uh, if we try to use one, probably we can reduce the noise collected by this one. The
Yeah,
noise,
but that is the amplitude, right?
yes, sir,
That's
the
the amplitude.
attitude part.
All right. So nobody's raising their hands. Maybe I'll
Sir,
ask another one. See,
Sir
Vanny.
Vanny Balois. But hi,
Hello.
I'm Vanny Balois from RIKEN, and thank you for your very nice presentation. I actually have a few questions, but maybe for now I'll just limit it to two. My questions are mostly related to resolution. So
Mm-hmm.
you showed that in your method you have a projector, and then you put a sinusoidal, I would say, film, which will act as your SLM. And does this regulate the resolution of your system, the resolution in terms of the smallest feature that can be resolved in your structure? So right now
Yeah,
you just used two large UP, but if you made the UP even smaller, can you still resolve the U and P using the same sinusoidal pattern, or do you have to increase the frequency of the
yes,
sinusoidal
yes.
pattern? Okay.
Yeah, okay. So for the first question, actually, for your question, I'm not really using sinusoidal films. So these are
Mhm.
patterns generated by a computer, and then you feed it to your projector,
Yes.
and then the scene gets illuminated by this structured light pattern,
Mm-hmm.
which has the shape of the sinusoidal, which is a 2D sinusoidal shape. Okay,
Yes.
so for a ghost imaging algorithm, what it does actually is to what you do is you project series of sinusoidal patterns of varying frequencies
Okay.
from low to high. So of
Mm-hmm.
course, if you only use sinusoidal frequencies with low sinusoidal patterns with low frequencies,
Mm-hmm.
what you're able to obtain in the Fourier spectrum or the low frequency details, which
Yes.
translates to the general details of the object, but not the smooth transition from, say, from black to white, which is a high frequency. Okay.
Yes.
So if you want to get the higher frequency signals, so what you
Mm-hmm.
do is you use sinusoidal patterns of higher frequencies. And if
Yes.
you want to retrieve
Mm-hmm.
smaller details, yeah, then you need to project um, all the sinusoidal patterns with frequency starting from low to high. And that actually depends on the size of the smallest detail in your test object.
And so the more sinusoidal projections you use, does it mean higher computation time, or it
Yes,
doesn't?
yes.
Yeah.
High or longer
Yes.
acquisition time, actually.
Longer acquisition time. Mm.
Longer acquisition time.
And actually, one more question is also related to resolution, but it's for your apodization factor for the three-dimensional Fourier ghost imaging. So you mentioned that, and you also showed very nicely that when you apply the apodization factor, the images become smoothened out. But have
Yes.
you ever tried using a sample wherein right now you're only using very smooth surfaces, but if you introduce some like fine features or some color like black spots, can the apodization factor also retrieve that information, or will it treat it just like some kind of noise and smoothen everything out, and then you can't see
Uh,
it anymore?
I haven't tried that yet, but
Mm-hmm.
usually, before applying a opodization technique, we first convert an RGB image to a grayscale one.
Yes.
In terms of the signals, actually, so the opodization technique, it's essentially
Mm-hmm.
a low pass filter. So, or yeah, a low pass filter. So it's only as you can see here with the image of the cone or of
Mm.
the hemisphere. Okay, as you decrease the size of the Gaussian mass, the image gets blurry. So
Yes.
you're essentially removing um the details with the details here in the spatial image
Mm-hmm.
with the higher resolution. So it may not be that uh, good to apply for images with smaller details, but you can actually play with the value of sigma, so as not to smoothen out the details that you need, the details that you want for the 2D image.
All right.
Okay, thank you.
Okay, maybe I have the last question. Can you describe an application where ghost imaging is particularly useful, a practical application where this kind of technique will be able to can be used?
Yes, sir. Actually, I wasn't able to put them here, but it has actually been used for several applications outside the visible spectrum, such as, for example, there's this group which did single pixel imaging of or computational ghost imaging of methane gas, so for detection of leakage, so using a very low cost single pixel imaging system. It has also been applied for ghost spectroscopy, digital ghost holography even, sir, and non-line of sight imaging. So the cool thing here is that the single pixel detector, as I mentioned earlier, it does not have to face the object itself or the target object itself. Um, it can be facing away from the object and still able to capture the signal or the structures of the signal if you have a reflective type object in front of it.
All
So,
right. So final. Why the phrase ghost imaging?
ghost
Why is
imaging
it called ghost?
uh, ghost imaging because you're using light that hasn't really physically initially interacted with the object. The computational ghost imaging actually started with quantum ghost imaging or quantum entanglement experiments, and the ghost imaging part was actually derived from that. It's imaging using light that has never physically interacted with the object, right? Or in this case, for the computational ghost imaging, the single pixel detector does not really have a resolution. You don't have an eye. You're like imaging without a camera. And any image captured by a computational ghost imaging is called a ghost image. You're imaging without 2D, the conventional digital camera that we know of. But instead,
All right.
you're just imaging using a single pixel camera.
All right. So with that, thank you, Ritz, for your presentation. So
Yeah.
let's now proceed to the next presenter. All right. So Lian,
Good morning, sir.
uh, can, can you now start sharing the screen?
Yes, sir.
Right. So Dr. Lian Dasallas is also from UP Diliman. He's in the Material Science and Engineering program of the College of Science. So Dr. Dasallas, you can start.
Okay, good morning, everyone, and thank you, PAASE, for providing a venue to share our work. The title of my work or the presentation is Computational and Experimental Works in Post-Tracer Ablation and Deposition, which is uh, basically the summary of the activities of our research group. Now, before I proceed, I'd like to thank my collaborators. First is Dr. Garcia, who is my dissertation advisor, and Dr. De Vero, who is my research supervisor. Previous collaborators include Ms. Lacaba and Mr. Patricio, who's now working in Maxim Integrated. And bulk of the work now is being carried out by our PhD students, Joseph, Jane, and Romil from NIP, and Jenny and Joy in the Material Science and Engineering program. Now, the work that we have been doing in our group is represented by these two simple part. First, we have the laser ablation, and the second part is focusing on the film deposition. So although these two processes looks like very simple, they are in fact rich in many, I would say, exciting physics when it comes to light matter interaction. Now, allow me to focus first on pulse laser ablation. This is a technique wherein portion of the material is removed from the surface, and this removal from the surface is accompanied by the generation of a luminous plasma plume, which is uh, list shown in this figure. This is a useful technique in many areas, such as surface patterning and in some chemical analysis part. Now, investigating pulse laser ablation is uh, a very active work now, and there has been many approaches to study it, especially when we use femtosecond pulse laser to provide the excitation. We have the molecular dynamics, hydrodynamics, rate equation, and two temperature model. These approaches can be applied depending on the material in consideration and the available computational resources. On our group, we focused first on metallic materials, and a very good approach to study ablation of metal is to use the two temperature model. And this model is written in this slide. Basically, what we have is a transfer of energy from the photon to electron to the lattice. This transfer of energy is described by these two coupled nonlinear partial differential equation. And we have C as our heat capacity, K as the conductivity, TE as our electron temperature, TL as our lattice temperature, and so on. The S in this equation is what we call the laser source term, and is useful and is typically given by this equation. As you can see, it is a function of the reflectivity and the laser fluence, along with the material properties such as the ballistic length and the penetration depth. Now, in most of the investigations done using the two temperature model, all of them assume that the laser pulse will approach the surface of the target at normal angle of incidence. But in some cases, the normal angle of incidence is not advisable. For example, in pulse laser deposition experiment, the substrate is located at the opposite part of the target, so you can't uh, put the laser path here. And on the other issue is what we call the plasma shielding effect. The laser is less effective when it passed through the laser produced plasma, and it will be more effective if it passed through the side. So what we did is to modify the existing two temperature model in cases where oblique angle of incidence is needed. So to do that, we just have to uh, place in the angle-dependent reflectivity, which is given by Fresnel equation, and we modify the fluence and beam waist to take into consideration the changes in the beam waist. So basically, the laser source term will look like this, and along with the boundary conditions, we can now do the pulse laser ablation modeling. To do that, we need to incorporate the physical properties of the metal, such as the optical and thermal properties. So in our work, we focused on copper, which is described by the critical point model of the dielectric function. The relaxation time is given by this equation, and the conductivity is given by this equation. The heat capacity and the electron phonon coupling factor is given by this equation. But if we are to put this equation into our modeling, the computation time will be longer. So what we did is we performed the polynomial fitting to the already solved electron heat capacity and electron phonon coupling factor in order to improve the computation time. So this is the result of our work. Typically, what the two temperature model gives us is the temperature of the electron and the lattice as a function of distance and on time. Shown in the left is the electron temperature, and on the right is the lattice temperature. So basically, at time right after the laser pulse hits the copper surface, the electron readily heats up, and after a while, the lattice will also increase its temperature. Now, as we know, the reflectivity is dependent on the angle and on the polarization. So what we did is to modify the angle of incidence and the polarization of the incident light. And as you can see, the electron and the lattice temperature decreases with the angle of incidence. And we see that the polarization also dictates the overall temperature of the copper surface. Okay, in fact, when we use p-polarized light, we can obtain a higher temperature compared to s-polarized light. However, the electron lattice relaxation time remains constant at almost constant at a different angle of incidence. We plot the maximum temperature as a function of the angle of incidence, and we see that they follow different cosine power behavior. So the one with p-polarized light is shaped like this, but with s-polarized light is shaped like this. Okay, the fitting factors such as the amplitude and the power of the cosine is given in the table. Now, the I would say the experimentally verifiable output of the two temperature model is to determine the depth of the crater formed by the pulse laser ablation. So in this slide, we determine the depth at different angle of incidence and polarization. And we see that they follow two different regime. At low laser fluence, the depth as a function of fluence follow a logarithmic behavior. However, at high laser fluence, they behave almost like a straight line. From our investigation, we have seen that the higher angle of incidence will result to a shallower, meaning less deep ablation crater. And since the temperature is higher for p-polarized light, we also observe a deeper crater when p-polarized light excitation is used. Now, when it comes to the diameter of the ablation crater, we determine them as a function of your polarization and angle of incidence. And as we know, when we do ablation at oblique angle of incidence, the beam spot will have a shorter axis and a longer axis. So basically, the diameter will be different for the short axis and on the long axis. However, we see that the size of the ablation crater, meaning the diameter, will increase with the laser energy pulse. And since the temperature decreases with the increase in angle of incidence, the resulting diameter will also change. However, again, when we use p-polarized light, we can obtain a bigger uh, ablation crater compared to the S-polarized light. So the result of our investigation here show that the angle of incidence will be an important parameter when we do pulse laser ablation at oblique angle of incidence along with the polarization. This will be important in some optoelectronic applications, especially if you want to do some more complicated surface patterns for different applications such as sensing. The material property, which is the energy needed to initiate the ablation, is also determined. What we have observed is it will be easier to do ablation for p-polarized light excitation compared to s-polarized light excitation, uh, which is an important uh, conclusion if we have to do some experiments such as pulse laser deposition. That will mean that the uh, polarization of the excitation has to be properly oriented in order to improve the deposition or the ablation efficiency. Now, allow me to move on with the deposition part. So this is a natural consequence of the pulse laser ablation. So since in pulse laser ablation, we have a material removal scheme. In the pulse laser deposition, we put a substrate opposite to the target surface so that the ablated material will recondense on the surface of the substrate to create thin films. Now, in the literature, the pulse laser deposition is usually done with different pulse lasers such as excimer lasers and Nd:YAG laser. However, in the late 80s, the technology of femtosecond laser, femtosecond pulse laser improved, and that enabled the use of femtosecond pulse laser in the deposition. Now, in the presentation today, I will focus on the two recent publication of our group in PLD. The first one uses nanosecond PLD. This one uses Nd:YAG laser to do ablation, and on the other one, we use femtosecond pulse laser in the deposition. Let me focus first on the nanosecond PLD. So in this work, we are able to produce iron oxide nanowires using pulse laser deposition. But the production of the nanowire from PLD, straight from PLD, is quite complicated or rather challenging. That's why we have to do what we call carbothermal oxidation of the iron oxide deposit. So in the first part, we deposited iron microsphere in the surface of silicon using Nd:YAG pulse laser. And after we obtained this iron microsphere, we placed them in a carbothermal oxidation chamber. We placed activated carbon at the bottom and heat up the system at different temperatures up to 800 degrees Celsius. So these are some scanning electron micrographs of the synthesized iron microsphere on top of the silicon substrate after the nanosecond PLD. So we can readily see that there's a presence of microsphere on the surface, and they tend to be bigger when we increase the deposition time, which is proportional to the number of laser pulses. Now, after obtaining the ion microsphere, we place them in the carbothermal oxidation chamber, and the result is we are able to produce iron oxide nanowires as large as 10 should be micron, 10 micron diameter. The nanowires are on top of the surface of the iron microsphere before. Okay, aside from the nanowires, we can see some nanopores and these nanoflakes. Okay, now these are some side view of the microsphere just to check the length of the nanowire produced, and the FTIR and the EDS confirm the presence of the iron oxide on top of the iron microsphere. The thermodynamics and the kinetics of the production of the iron oxide from the iron is quite interesting, because we think that the presence of Fe3O4 as a metastable phase is needed in order for the iron oxide nanowire to grow. So the tendency is for this metastable layer to initially form on the surface of the iron oxide, on the iron microsphere, and the iron will diffuse from the microsphere towards the surface, producing iron oxide nanowire. So that ends our work with the nanosecond PLD. Now, this nanosecond PLD, as we have observed in the previous work, produces micron-sized structures on top of the substrate. Now, it turns out that when we use femtosecond laser pulse, we can observe larger amounts of smaller deposits, and some of them is nano has a size in the nanometer range. So what we did is we used the femtosecond titanium sapphire laser. That's a femtosecond pulse laser to do the deposition. And in this case, we used Nd:YAG laser crystal as our target for the deposition. So this is the X-ray diffraction patterns, and we see that the produced film has a preferred orientation in this direction, and the structure can be improved by application of the heat treatment. So this is the surface topography of the as deposited film, and we can see that the variation in height is within few tens of nanometers, which indicates the production of nanoparticles. Now we applied two different heat treatment. The first one is the in situ heat treatment, and the other one is the post-deposition heat treatment. Just to check its effect on the topography of the deposited film. So we can see that both heat treatments tend to decrease the size of the deposited particle with the increase in temperature, and more islands can be found at post-deposition heat treatment. In order to explain this result, we we used the thermodynamics approach in describing deformation of the thin film. So we have here the volume-free energy of the system as a function of your pressure and temperature. Essentially, when this volume-free energy decreases, the three-dimensional island growth is preferred. And when we increase this volume-free energy, the two-dimensional monolayer growth will dominate. Now, to compare the two heat treatments, we parameterize the pressure as a function of your alpha and beta. Now, in the in situ heat treatment, we are applying heat treatment while we deposit the film. But when we do the post-deposition heat treatment, we have a two-step process. We first deposit the film, and then we apply the heat treatment. This differences in the application of temperature uh, changes the overall behavior of the volume-free energy. That's why we are able to see more island growth in the post-deposition heat treatment, mainly because the decrease in the free energy is greater compared to the in situ heat treatment. We also tried to do parametric investigation using different background gases. So for example, we have a nitrogen background gas. And when we increase the nitrogen background gas pressure, the tendency for the particle is to uh, coalesce with one another. And we explain it again using the volume-free energy. Okay, but when we use oxygen background gas, we did not observe the same behavior. And we think it's because of the chemical interaction of the oxygen with the Nd:YAG laser as it is being deposited. This is the reflectivity, just to measure the optical band gap of the deposited film, which is quite close to the expected band gap of the Nd:YAG laser crystal. Now, before I end my presentation, allow me to share to you some of the current activities of our group. First is we are now working to extend our work to non-metallic materials. For our first move is towards semiconductor material. And since this is a different material, we can expect different physics of ablation. In fact, for metallic material, it is often enough for us to describe it in terms of the temperature. But when it comes to semiconductor, we have to take into consideration the carrier generation. And this work is currently being done by our colleague, Joseph. But what's interesting when we talk about semiconductor material is the cases where there might be an ablation, but it is not thermal in nature. As long as we pass what we call the critical current density, the ablation can occur. And this is the case when we use multipulse in our simulation. We can see the incubation effect, that the higher the number of pulses, we can accumulate the temperature and the carrier density. On the transfer mechanism from the ablation to the deposition part, this is currently done by our colleague, Romil Emperado. But the point of this investigation is to investigate the dynamics of transfer from the ablation to the deposition part. And as we can see, this part will play an important role in the deposition because of the physics and chemistry of the transfer of material from the target towards the substrate. For example, what will happen if we put a physical mask on the path between the target and on the substrate? Essentially, a majority of the deposited material will be placed opposite the mask, and we can expect some movement of ablated particles from the side of the mask. On the last part, we are interested in further improving the temperature model. And in this case, we are curious what will happen if we modify the laser source term. In all of the computational researches done in modeling ablation of metal, they always assume a Gaussian intensity profile of the laser source term. Now, what will happen if it's not Gaussian in nature? So we have a Lorentzian and hyperbolic secant beam profile, and as expected, they look like Gaussian. However, we think that the differences in the uh, profile of the intensity will manifest itself if we have larger amount of pulses in the ablation part. And on the other hand, experimentally, it's not perfect Gaussian. It's not always perfect Gaussian. So what we did is to do some multi-term Gaussian fitting in the laser spectra. And we observed that aside from the main pulse, we have some side band. What we have here is a pre-pulse and post-pulse distribution. This is important because in many experimental works, people will try to explain it by assuming that there's a single dominating pulse on their calculation. But in reality, there are some energy before the main pulse and after the main pulse. And this energy will drastically change uh, the energy distribution on top of on the ablation part. Before I end my presentation, I'd like to thank the Natural Science Research Institute, the UP system for the Enhanced Creative Work Research Grant, NRCP, and for the thesis and dissertation grant of the OVCRD of UP Diliman. With that, I'd like to end my presentation. Thank you very much.
All right. So thank you, Lian. So we have time for one or two questions from the panel. Anybody?
Sure.
Hello, Ate Bani.
Hi,
Sir
Lian. Nice
Balois.
to see
Okay.
you. I
Nice
have
to
a
see you too.
question about the angle of incidence of the laser.
Yes,
And
ma'am.
does this affect the quality of the surface quality of the deposited material on your substrate?
When we're talking about the angle of incidence dependence on PLD,
Mhm.
uh, we did not do a systematic investigation on that. But when it comes to ablation, uh, there is definite changes in the surface morphology and topography of the target, but not on the target. The question on its effect on the film is still an open question. But thank
Okay.
you for the research idea.
All right.
Good luck.
So
Thank you very much.
we have another question from Dr. Hermosa.
Hello,
Hi.
sir.
Hello, Lian. Thank you very much for the for the presentation. Okay, I have two questions.
Yes,
Maybe it
sir.
will have three. It will be three or four. But the first question is it intuitive? Because what you did is to look at the ablation, different angles for a particular metal. Is that correct? A particular
Yes,
metal.
sir.
Intuitively you have a more absorption for a certain angle with depolarized light.
Yes, sir.
Well, does it correlate nicely, or there is some factor to it?
Uh, some Japanese group did a systematic experimental investigation on the dependence of the crater to the angle of incidence and polarization. And they conclude that it's more efficient to use p-polarized light, and they attribute it uh, to the resonant, sorry,
Yes, yes.
resonant absorption of the laser energy on the target. So in terms of correlation, perhaps pwede ko sabihin, I can say that it has been observed experimentally.
So in relation to that, um, for semiconductors,
Yes, sir.
it also has some, if you look at the displacement, the D, it's just one proportional to 1 over also a resonant frequency, right? Um, in the Drude model, uh, wouldn't you have the same results for metal and semiconductor?
That's a good question. Right now, I would say it's an open question. The good thing is it can be done easily. I believe Joseph has a working code now, and I have a simple modification on the laser source term. So the safest answer that I can say is please wait for the result of the
All
computation.
right.
But it can be easily done, sir.
Okay, thank you very much.
Thank you. Thank you, Dr. Hermosa, and thank you, Lian, for the
Thank you, sir.
presentation. So we will now proceed to the last presentation for this session. So let me now call on Dr. Vanessa Balois to start.
Okay. All right, I hope you can all see my slides. So good morning and thank you very much for the opportunity to present in this online conference, especially PAASE and also Dr. Almoro for extending this invitation to me. And a little bit of trivia, I recently got married. So
Yay!
my actually new surname is Oguchi, but for now I'm still Maria Vanessa Balois. But after the documents are all finalized, it's going to change soon. But anyway, thank you for the kind introduction. And I'd like to give a presentation wherein we show the development of near-field scanning optical microscope systems for nanomaterial characterization. And I am affiliated with RIKEN, which is a research institute here in Japan. Now, to give a short introduction, what is my team? What is the Innovative Photon Manipulation Research Team? So our team focuses on creating sub-wavelength structures which we make and use to observe or measure certain properties of our material or of the sample material. And our research is basically split into two kinds of research. The first research is by making these and designing these structures and then using them for practical applications. And we call these sub-wavelength structures metamaterials. And one of the applications of our lab right now are mainly absorbers, sensors, and also surfaces for light manipulation. And a little bit of trivia, some of you may see a familiar face here in my slide. We have one Filipino student from UP, Dr. Hermosa's student, Miss Cherry May Olaya, and she's currently finishing or doing her PhD research in our lab here. Now, the second aspect of our research is that we make these sub-wavelength structures and then we use them to observe near-field light matter interactions. And for these light matter interactions, one of our group mates or lab mates is studying chirality, while as for me, I study or I use a sharp metallic tip, which I use to scan and also observe the very local physical chemical properties with resolutions beyond the diffraction limit. And this technique is called near field scanning optical microscopy. And our team is headed by Dr. Takuo Tanaka, who is an expert in both metamaterials and also plasmonics. Now, going to the meat of the presentation, I mentioned we are using a technique called near-field scanning optical microscopy. Now, there are a variety of, so it's a big family, and one particular member of this family I'm using is tip-enhanced Raman spectroscopy. For those of you who are not familiar, tip-enhanced Raman spectroscopy combines a tip or a plasmonic metal tip, wherein when you shine laser light on that tip, a nano-confined light source is generated at the tip end due to photon confinement and leads to a tip-enhanced electric field. And combining this tip with what we call Raman spectroscopy, which is a very powerful technique to distinguish the chemical properties of a sample, that if you image each single peak from the Raman spectrum, you can actually get various kinds of information. Basically, Raman spectroscopy is done in the far field wherein you do a large scan of the sample. Here in this image, it's actually 10 microns by 10 microns. But for tip-enhanced Raman spectroscopy, we are actually interested only in 1 pixel of that entire image. And then in that 1 pixel, we want to image that small pixel to get the very local properties of our sample, which is why TERS has been dubbed that it is an analytical technique with both high chemical sensitivity and also high spatial resolution. Now, in our team, we want to not only develop, well, the main goal is to develop the system. So there are three factors which we want to develop, but there is one core idea behind everything. It is simply making the invisible visible, which is actually the main purpose of a microscope. And in our terms, we can think of it, instead of a microscope, it's a nanoscope, because you want to see nano-sized materials. Now, the three important aspects we are trying to tackle now are: first, chemical sensitivity; second, spatial resolution. And once we have these two, we want to make our results repeatable and reproducible, which is why we also emphasize on system stability. Now, the flow of this presentation is I will be first focusing on chemical sensitivity and how it goes along with the system stability for one particular application which I developed during my PhD, which is tip-enhanced terahertz Raman spectroscopy. And the other half of the presentation is dealing with high spatial resolution, which in turn, because of the high system stability, can also enhance the chemical sensitivity of the entire system. So let's dive into everything else. Now, tip-enhanced Raman spectroscopy is a very great technique, but the main limitation is it is limited only to the fingerprint region. Fingerprint region means basically the 200 to 2000 wave number of the Raman spectrum, if you look at the spectra. Now, the interesting part is, so far, the lower frequency regime, which we call terahertz Raman. Please do not confuse this with the terahertz wavelength, which is in the far infrared. So that's totally different. Now, here, terahertz simply means low frequency, and this is basically from 5 wave number to around 200 wave number. So these frequencies are near the Rayleigh line or excitation line. And here we can simultaneously detect both the Stokes and anti-Stokes Raman. And these aspects I will show you in this slide. So the advantages of using tip-enhanced terahertz Raman spectroscopy and also the terahertz or low frequency Raman that you can detect are: for 2D nanomaterials, which are layered, they're very useful to find out the number of layers of your sample, for example, graphene or molybdenum disulfide. And then another aspect which is interesting is that using these low frequency Raman modes for carbon nanotubes, you can determine the diameter and also the chirality based on what we call the radial breathing mode. Now, I think for me, the most interesting part for low frequency Raman is in the biological applications, particularly for medicine. Now, take, for example, carbamazepine. And if you look at the fingerprint region or the 200 to 2000 wave number, if you compare form 2 and form 3, two kinds of carbamazepine, the fingerprint region or the Raman signature is totally identical. So it's very difficult that you don't know, based from this fingerprint region Raman signal, if it's a form 2 or a form 3. But if you look at the low frequency, they are totally different. So here you can clearly determine which carbamazepine is in the form 2 and which carbamazepine is in the form 3. Now, the research which I'm tackling which I tackled, is mainly about the problem of heating because of the enhanced electric field that is generated at the tip end. And how can we extract this nanoscale or nano volume temperature and use it for practical purposes? Now, low frequency Raman is useful for temperature determination because you can actually calculate the temperature based on the Boltzmann distribution and also the intensity ratio of both the anti-Stokes and the Stokes Raman. And by doing it via experiment, obtaining the anti-Stokes and the Stokes intensities and then crunching out the numbers based on this equation, you can actually calculate the temperature at the tip end, which is more or less the temperature at the tip, at the sample. Now, the setup we used is a conventional atomic force microscope system where we have a tip, which is either gold coated or silver coated, and depending on your laser illumination. And then the special part of our sample, or not sample, but our setup, is we use special notch filters which filter out the Rayleigh signal and make it possible to detect both the Stokes and anti-Stokes frequencies simultaneously. Now, as a result, we were able to calculate or to extract the anti-Stokes and Stokes Raman from the carbon nanotube. And from there, we were able to detect sample temperatures less than 100 degrees Celsius. Now, one thing I have to point out here, since I was so excited about the temperature, is please look at this image over here, which is the terse image and also the topography image. Now, the other powerful thing about terse is that you can get both the chemical information and the topographical information simultaneously. And note here that this is actually 2 carbon nanotubes, and the scale bar here is around 100 nano. So we can actually see very, very thin carbon nanotubes, both in the terse image, which is the Raman imaging of the G band, and also the topography. And lastly, going back to the temperature, we found that you can control the temperature, well, low temperatures less than 100 degrees Celsius by simply controlling the input power. And with this, we found that this is very much an exciting topic to pursue. And right now, we are trying to improve the detection sensitivity of low frequency Raman by also increasing the number of filters or notch filters in our system so that we can have a better signal to noise ratio. So here you can clearly see from the 2 notch filters to the 4 notch filters, particularly at the center, which is close to the Rayleigh line at 0 wave number, the peaks, especially in the anti-Stokes, can be clearly seen for the 4 notch filters that were used. And aside from that, of course, we want to have better chemical detection by improving the instrumentation, but we also want to have the system to be more stable to do better or even long-term measurements. Now, we also have a temperature booth installed wherein it controls the temperature, and the error is around plus minus 0.1 degrees. So the red line is inside the booth and the blue line is outside the booth. And I would like to personally thank Dr. Dasallas because he was also very instrumental in improving the condition of this temperature booth during his stay as an intern in the Nanophotonics Research Laboratory. And we found that we were able to create a very nice, stable temperature environment to prevent what we call thermal drift. And another factor which we want to consider so that we can also shift to what we call long measurement times is that we want to ensure that the laser focus on the sample is always at focus. And to do this, we have implemented this system wherein we use a capacitive sensor, which helps maintain the focus spot position of our objective lens. And the stability of this system is plus minus 1 nanometer. Now, to clearly see how this autofocusing system works, let me show you this very nice slide. Without the high stability system, you can see that as the time increases, the temperature of the room also increases, and that also causes some defocusing because of the changes in the environment. And over time, at first, at the start of the measurement, you still have a more or less focused image, but as the time goes by, it becomes very much defocused that you cannot anymore identify what kind of structures you are trying to make or to image. But with the high stability system, you can clearly see these strained silicon nanowires, which are nicely spaced from each other. But so far, the system is only working for what we call conventional microscope, which is just far field measurements, wherein there is no tip involved. So we want to integrate these two systems together as a next step. Now, the other aspect of the system is, so a while ago I mentioned an atomic force microscope, and now we also have another system which is called a scanning tunneling microscope. So they're both part of the scanning probe microscope family. However, the mechanisms are quite different. And unfortunately, I do not have enough time to differentiate both of them, but we use both of these techniques for our TERS experiments. Now, the STM TERS system is also, we improved the environment by putting our system inside a metallic environment control chamber, wherein, as you can clearly see here, inside the chamber, the temperature is very much stable and the humidity does not vary much. The humidity varies only maybe plus minus 1 degree RH, 1% RH. But outside the chamber, you can see the very dramatic change of the temperature, which is very not good for our system. And we also, this system can also be compatible with well, nitrogen. Like you want to purge nitrogen into the system, and when nitrogen is purged into the system, the humidity actually goes to zero, which is very nice for samples which are very much uh, well, sensitive to the atmosphere, particularly highly oxidizing samples. Now, let me shift from the AFM to the STM. Now, the beauty of the STM is that you can control very well the tip sample distance, which means that the stability is very nice. And using this system, we were able to get a very high spatial resolution of 0.7 nanometers. And this is currently the world's highest spatial resolution for ambient TERS. Now, the sample that we studied is simply a gold substrate with gold one-on-one substrate with a monolayer graphene, which is pristine, wherein there are no defects. And we scanned a large area here of 50 microns by 30 microns, but the actual scanned area is just this small area over here. Now, the very nice thing about not only having high spatial resolution is we found that if you have highly confined light, you can alter the Raman selection rules. And this means that you can maybe change even the chemical sensitivity of your system. And this was shown using surface enhanced Raman spectroscopy, which is simply, well, it's diffraction limited. So the results by our collaborator showed similar work wherein they were able to observe what we call forbidden modes, which are associated with defects on graphene, but their sample did not have any defects. It's a pristine sample, but they were able to still observe these peaks. And the main question is why? And we think that this is because of the highly confined field that decays very quickly. And this is a field gradient, which in turn also changes the Raman selection rules, which means that we indeed are now making the invisible visible, because phonon modes which are not supposed to exist are starting to show themselves, particularly these defect-related peaks, which are not supposed to be there because our sample is defect-free. And we think that this is due to the non-vertical optical transitions, which are caused by our near-field system, which causes the causes it to actually activate these forbidden modes and also detect them. And the nice thing about this is, so okay, we have high resolution system. We can actually also do imaging because we can also see the topography. And we found that we can also observe these nanoscale strain variations. Note that this image is only actually 23 nanometers by 14 nanometers in height. And we found that these nanoscale strain variations can be directly observed. But currently, they could not be directly observed because of the diffraction limit, and they can only observe it via the broadening of certain Raman peaks. But now, using our system, using TERS, we can now also do such kinds of high-resolution imaging and also obtain very small information with high chemical sensitivity. Okay, so in a nutshell, so to summarize my presentation, the main goal of our team is to use sub-wavelength nanostructures to observe and also see certain things from our sample. And basically, we want to make the invisible visible. And this is possible by using a technique, well, in my case, called the near field scanning optical microscope, wherein we use a very nice technique called tip-enhanced Raman spectroscopy and tip-enhanced terahertz Raman spectroscopy for high chemical sensitivity. And so far, using the STM, we are able to obtain the sub-nanometer spatial resolution, which in turn can unlock certain Raman modes, which can in turn also increase the chemical sensitivity of our system. But all of this, or these two, of course, should go hand in hand with high system stability. Without the high system stability, we cannot get reproducible and reliable results. So thank you very much for listening to my presentation. And to end my presentation, I would like to acknowledge my research collaborators, both in the Surface and Interface Science Laboratory, and also particularly Dr. Francesca Celine Catalan, who helped in the work for the TERS temperature measurements for tip-enhanced terahertz Raman spectroscopy, and also Professor Riichiro Saito of Tohoku University for the very insightful discussions regarding the transitions of the forbidden modes for near field due to near field excitation. And I would like to thank these funding agencies for their financial support, because without the financial support, the progress of research will be very much slower than it is. So thank you very much, and I welcome your questions.
Thank you, Vani, for the nice presentation. We have time for maybe one or two questions. So we have a question from the chat box from Mr. Raymond Birtudaso. What do you think the instability occur during analysis?
During analysis, so I would say that analysis as in processing the data, if that's my understanding, for data analysis, we usually take into consideration the errors due to the experimental system, and these errors are very much accounted for. We know the for the spectrometer, we actually know the error margin for the measured Raman peaks, and also we also do some filtering also for the imaging to make sure that the signal to noise ratio is also suitable and gives a clear image of the image data. So I'm not sure if that clearly answers his question or if that's the gist of his question.
Okay, thank you, Vani. We have a second question from Dr. Dasallas.
Yes.
Hello, Atibani. Thank you
Hi,
for the
Lian.
exciting presentation again. I'm just wondering, is it a conscious effort to make the temperature lower in your measurement, or higher temperature is better?
Okay, so that's a very good question. So currently, my research is focused on room temperature. So we're just dancing around the values of around 19 degrees to around 23 degrees.
I'm talking about the temperature on the enhanced field at the tip.
Okay. So yes, the I guess the key point for the temperature underneath the tip is for temperature sensitive samples, particularly biological samples, the lower temperature is better because of you can damage the surface, let's say, of a cell or of a molecule, and then, or you can also actually inadvertently cause chemical reactions simply by applying heat. But for more robust samples, which, so for example, graphene or maybe silicon, as long as the heat temperature does not cause a Raman shift due to heating, that is still okay. So because for Raman spectroscopy, we usually observe the shift of the Raman shift. And this shift can be caused by strain, by interaction with another molecule, etc. But we want to make sure that shift is simply due to the interaction or due to the strain experienced by the sample and not due to the heating, which can also cause shifting. So for those kinds of experiments, we still have to do a power Raman shift calibration to make sure that the Raman shift is still constant at a certain power. But once it starts this shifting because of higher power, that's when we say, okay, this power is not good. So that heating caused by the tip is also not good for the experiment. So yes, I hope that answers your question.
All right. So, Bani, marami kang fans. So, for the last, we have Dr. Tarun.
Sir Al, hello.
Hello, Vani. Congratulations.
Thank you, sir.
Wow, it's been a while. So,
yes, sir.
Magtanong ka na.
Ang tanong ko ay, so in the resolution of 0.7,
yes.
Do you know what is the distance between the tip and the sample?
So right now, a quick answer to your question is no, but we are assuming that it's around 1 nanometer. But we haven't.
Is there a correlation between the tip distance and the spatial resolution?
Actually, that's a very good question. That's the next step of the research. So right now we're trying to further improve the stability of the system so we can do some tip sample distance and observe the evolution of the Raman peaks by increasing yes. Thank you very much.
Okay.
So, thank you very much. So, let's have a group photo. And those who are in the panel, can you show your beautiful faces? Ritz, Jay, Jack, Nori, are you there? Yeah. So let me just say a few words. So this is a good opportunity for physicists and engineers to collaborate with the guys in the biochemistry. Hi, Nori. So our presentations will be curated in the PAASE website and social media platform so that the researchers in the other disciplines can relive this momentous session. All right, so let's have a group photo. Smile. 1, 2, 3. Okay, so si Jack. Jack, one more. 1, 2, 3. Thank you, guys. Thank you for our presenters. Bye-bye.
Bye-bye.
Bye, Nori.
Bye, Sir Al.
Bye.
Bye, congrats.
Bye. Thank you. Congratulations, Ate Vani.
Bye, Sir Val.
Okay, bye. Thank you. We'll end now.